Okay, I'm back, and now we want to do part 2 of the lab, which is on springs. Now, you're still going to be measuring the frequency of the spring using this formula here. And so this time you're going to have a mass on a spring, and you're going to pull it down and then let it go, and it's going to bob up and down. So you're going to let it go up and down 10 times, and you're still going to be measuring the amount of time it takes it to do it in. So you are going to be using this formula. But notice that there is a different formula for calculating the frequency of a spring. And so it's still got the 1 over 2 pi. It still has a square root thing, but it has this thing here, which is called the spring constant. The spring constant is how stiff is the spring. So like, for example, a rubber band has a very, very small spring constant. It's very stretchy. It's not stiff at all. On the other hand, a shock absorber for a car is a very, very stiff spring. So it would have a large spring constant. So that's what this thing here is. Now you're going to have to calculate the spring constant before you can use this formula. And I'll show you how to do that. And then M is going to be the mass that you put on the end of the spring. So that's going to be what we're going to be doing here. Okay, so we're going to go to FET, and then this time it's going to be masses and springs. So when you go there, this is what you're going to see. Okay, now I'd like for you to change the mass to 150 grams. So our M is going to be equal to 150 grams, but the problem is that that is the wrong unit. We need to use kilograms. And so in order to change from grams to kilograms, we need to divide by 1,000. So there's 1,000 grams in 1 kilogram. So if you want to actually see how this is being done here, we can write this using a conversion factor so that there are 1,000 grams in 1 kilogram. And you see the grams cancels out, and we're going to divide by 1,000. So this is going to be 0.15. And then now that is going to be in kilograms. So this particular formula up here, you have to use kilograms for your mass. Okay, now we're going to take this mass here, and we're going to put it up there, and you can see that it's going to stretch it out. Okay, and actually let's put a lot of damping on it, so I need for it to come to a stop. Alright, so there. So you see that by putting the mass on the end of the spring, it stretched it out. Now we can, so now I'm going to take this off, and put it back. I need to know what was the original length of the spring. So if I go over here, I can get a ruler, and I can put it up there, and you notice that this is going to be in centimeters. So that's going to be the length of the spring in centimeters. Now, I can't really read that very well, so I'm just going to make up a number. So it looks like, I can't read that, 50? Okay, sounds good to me. So I'm going to say that this is L sub 0. The original length of the spring is going to be equal to 0.5 meters. Okay, now I want you to be a little bit more precise than that. So you want to measure from here down to here. That's going to be the original length of the spring. Okay, then we're going to take the weight and we're going to put it on there and make it come to a stop there. Okay, now it's stretched it out, so it's a new length. So let's just say, for the sake of argument, that it is 0.8. So L, so the new length is going to be 0.8 meters. Now we need to find the change in the length of the spring. So delta L, so that's the change in the length, is we're going to take these two numbers and subtract them. So we get 0.3 meters. Now you're going to be taking all of this information and you're going to be putting it into this chart right here. So you got the measured mass, and now we haven't got this calculated weight thing. So what we need to figure out is the spring constant. So later in the course, we're going to learn about the force on a spring. If you pull a spring out, the spring tries to pull you back in. So there is a force F, and that's the force on a spring, is equal to the spring constant, and then how far does the spring stretch, delta L. So this is our formula. So if you pull it this way, the force is going to try to pull it back. Now, what is causing it to stretch? It's going to be gravity. So you see, the gravity is pulling down on the spring. So that force is the weight. So the weight of an object is mg, where m is the mass that you're hanging from the spring, and then g is that 9.81 thing. It's not grams. So this doesn't stand for milligrams. So this is the mass in kilograms. This is that 9.81 thing. Okay, so that's the force that's pulling down. This is the force that's pulling up. So we set them equal to each other. So therefore, we're going to end up with C delta L is going to be equal to mg. Okay, so there's our formula. And now what you need to do is, you'll know what this number is, you'll know what the mass is, you'll know 9.81, and then solve it for the letter C. Okay? And so that's going to be your spring constant. And so you will put that, let's see, we got down here the calculated spring constant. So you will put that number here. Okay, now that you've got that, then you're ready to actually do the lab and calculate the frequency. And we will do that in our next segment.